Hello everyone, this is Dr. Suman, Associate Professor, Department of Civil Engineering, AJIT Mangalore. Today I will be dealing with the problems of support reactions. Already we have started with the support reactions. Today I will be dealing some more problems based on the concept of support reactions. In that first problem, calculate the support reactions for the cantilever beam shown in the figure. So this is a given cantilever beam which is fixed at one end and free at the other end. You may see two loads here other than the point load 80 and 30. There is a triangular uniformly varying load and uniformly distributed load acting here. First you need to find out the point load for this as well as this one. So when it is a uniformly varying load, you have it here from 0 kilonewton per meter to 2 kilonewton per meter it is acting. So it is acting over a distance of 2 meter. To convert this into point load, so it is nothing but it is a shape of a triangle. So we usually do half into base into height. You'll get 2 kilonewton. Now we need to know where does this point load act. It acts at a distance of, it acts on the CG of the triangle at a distance of 2/3 L from this point, 1/3 L from this point. L is 2 meter over here. So it is 2/3 of 2, 1.33 meter from this side, 1/3 of 2, 0.67 from this side. So when you plot your point load, it is at 1.33 meter from this side, 0.67 meter from this side. Next, coming to the uniformly distributed load 4 kilonewton per meter, that is acting over a distance of 3 meter. So 4 kilonewton per meter into 3 meter gives you 12 kilonewton is the point load. Acts at the center always. If this is 3 meter, acts as 1.5 meter. Okay. Next is for the entire beam, apply the conditions of equilibrium. Summation f of y is equal to 0. So here this is a fixed support. In the fixed support, it prevents the motion of the beam in the x direction, in the y direction and in the circular direction. Okay, that is a rotational motion is prohibited. So you have RAX, RAY and the moment MA. Now apply summation f of y is equal to 0. So it is RAY plus 80 sin 30 in the y direction. So it is minus sin 80 sin 30 minus 2 minus 12 and minus 30, which is equal to 0. Further simplifying, you get RAY as 84 kilonewton. Next, you can apply the summation f of x is equal to 0. So RAX minus 80 cos 30, no other x forces. So RAX is equal to 80 cos 30. Simplifying, you will find out RAX. Next, we are supposed to find out what is this moment about this point A. So apply the summation of moment about the point A and find out what is this MA. So I take the moment about the point A and each force with respect to each force and the perpendicular distance, that is the moment. 80 sin 30 in the clockwise direction towards the point A into 3, 2 into 6.33, 12 into 3 plus 4, 7, 8.5, 12 into 8.5, all are positive. 30 into the whole distance, that is 7, 10, 12. 30 into 12 in the clockwise positive direction. So finally you get the moment M, which is equal to minus 594.667. In the previous problems, if I take the moment over here, about this point, there was no couple acting here. That is why MA did not appear. Whereas here you have this MA here in the fixed support. That is why you are getting MA is equal to this much. Okay. So, but we have got a negative answer. What does this mean? This means that you had taken it as clockwise. We got a negative sign, means it is actually in the anti-clockwise direction. Next, determine the reactions at the supports A and B for a beam loaded as shown in figure. So there is a 40 kilonewton point load acting here. There is a UVL, uniformly varying load. It is trapezoidal in figure, and there is a hinged support and a roller support over here. Actually this is hidden here. This is also roller support acting here. So for a hinged or a pinned support, you have two reactions, that is RAX and RAY. Why the RAX is in this direction? Because in this particular problem I have assumed that the beam is moving in this direction. Because the force is being applied here, the beam can move in this direction or in this direction. The horizontal motion is objected by applying the reaction in this direction. We know that hinge opposes the vertical motion as well as the horizontal motion of the beam. So either you apply in this direction or you apply RAX in this direction. At the end you get a negative answer for RAX, then it means what sign convention you have taken, either RAY or RAX, are wrong. It is in the other direction you are supposed to apply. That is what it means. So now for this problem I am taking in this direction and this direction. Okay. And the point here B, roller is acting, only one normal reaction will come into picture, which is known as RB, and I have applied it over here. Okay. Then simplify this figure. Now this trapezoidal is there, so either you can use it, you can apply the trapezoidal formula and find out where the point load will apply, or you can split it up into a rectangle and a triangle load, because we know how to find out convert the UVL and UDL. Separately we have done. This is a combination of both the problems. That is, for the rectangular or the uniformly distributed load, it is 20 kilonewton per meter into 3 becomes 60 kilonewton, where it acts, the CG of rectangle always lies in the center. So 1.5 meter from here, 1.5 meter from here. So point load will be acting at a distance of 1.5 meter from the point A. For the triangular load or the uniformly varying load, you have half into base into height will be a conversion for the point load. This is varying from 0 here to 40 kilonewton here. How 40 kilonewton came here? Up to this point is 20, total is 60, so the remaining is 40. Half into base is 3 meter into 40, which is equal to 60 kilonewton. Point load acting here, CG of the triangle, will lie at a distance of 2/3 from this point and 1/3 from this point. So 60 kilonewton is acting at a distance of 2/3 of 3, which is nothing but 2 meter. 1/3 of 3 is nothing but 1 meter from this end, from the point B. Now apply the conditions of equilibrium for the figure. This is the free body diagram for the figure, for the given figure. Apply the conditions of equilibrium, summation f of x is equal to 0. So 40 cos 45 minus RAX is equal to 0. Therefore RAX is equal to 28.28 kilonewton. Summation f of y is equal to 0. RAY minus 40 sin 45 minus 60 plus RB is equal to 0. Therefore RAY plus RB is equal to 148.284. This is covered over here. This thing is covered over here. Under this there is minus 60 minus 60. Okay. So you'll get 148.284. Next, apply moment with respect to the point A. About the point A, about the point A, take the momentum. So this force 40 sine 30 in the y direction. With respect to A, it is anti-clockwise. So minus 40 sine 45 minus 40 sine 45 into 1 meter distance. Next one is 60 into 1.5 with respect to this point. 60 into perpendicular distance 1.5 clockwise. So it is 60 into 1.5 plus 60 into 2 plus RB into perpendicular distance 3 meter anti-clockwise. So minus RB into 3 minus RB into 3, which is equal to 0. Therefore RB is equal to 77.238 kilonewton. Now you know RB, you know RAY and RAX, you know RB, substitute RB here, find out RAY, you know RAY, you know RAX. So RAX and RAY, if you know, they have asked you what are the reactions at point A and point B. In point B it is RB, find out the resultant of RAX and RAY, you will get RA acting at an angle of theta with respect to RAY. How do you find out the resultant of two forces? Resultant of two forces RA is equal to square root of RAX square plus RAY square. So you find out this, you get RA like how we did in the first module. Find out RA, find out the theta which is making with respect to RAY. Okay, so thus solved. Next problem, it's a combination of triangle and the trapezoidal load with the roller support at point B and hinge support at point T. You are supposed to find out the support reactions for the following figure. Here, whatever reactions are developing here, you are supposed to find. Before that, convert this uniformly varying load into a point load. For the triangle, 20 kilonewton per meter is acting here over a distance of 6 meter. So when you convert 20 kilonewton per meter, 20 into 6 into half into base into height, you get 60 kilonewton, which will act at the center of this triangle. Okay, so it is acting at 60 kilonewton is acting at 3 meter here from here. Okay, next coming to the trapezoidal load, that is you split this trapezoidal load into the rectangular load and the triangular load. Find out the point load like same in the previous case. For the rectangular load it is 10 into 5, 50 kilonewton acting at 2.5 meter it will come. For the triangular load it will be, so 50 kilonewton acting at 2.5 for rectangular or the uniformly distributed load. For the uniformly varying load, you will have half into base 5 meter into 20. How 20 here? Because 10 is here, 30 whole minus 10 remaining from here to here, it is 20 kilonewton per meter. So you will get 50 kilonewton. 50 kilonewton acting over here. That is 2/3 of L from this point. 2/3 of L from this point. 1/3 of L from this point. So you will get that as 3.33 and 3.33 meter, 1.66 meter. Okay. So substituting all this, draw the free body diagram. Here only one reaction will come, roller support By I have written, R dy, R dx will come into picture. Next, summation f of x is equal to 0. So in summation f of x is equal to 0, one of the conditions of equilibrium, you will get R dx minus R dx. Any other force acting in the horizontal direction? No. So which is equal to 0. Therefore R dx is equal to 0. Summation f of y is equal to 0. R by plus R dy minus 60 minus 50 minus 50, which is equal to 0. Therefore RBY plus RDY is equal to 160. Now find out the moment. You know what is RDX, you do not know what is RBY and RDY. So apply the moment about the point, any point D, B or D. Applying the moment about the point B, applying the moment about the point B, we get here 60 is passing through this, By is passing through this, don't consider that. 50 kilonewton into 5.5 clockwise positive. 50 kilonewton into 3, 2.5, 5.5, 5.5 plus this 2/3 of 5. You get 6.33. Next, r dy at a distance of 8 in the anti-clockwise direction. So it is minus r dy into 8 is equal to 0. Therefore, r dy is equal to, you will get this answer. R dy you found out, find out r by, which is equal to r by you found out. So r dx is 0, r dy is some value, that is 73.958. Find out what is the resultant of r dy and r dx here. Rd is equal to square root of r dx square plus r dy square is equal to 73.958, which is the force Rd acting at an angle of theta with respect to Rdy. Rby anyhow you have calculated. So these are the reactions at the point B and D. Okay. Next problem. Find the support reactions at point A and point B. B is here, okay, this point, for the beam loaded as shown in figure. This is a pinned or hinged support. How many reactions have developed here? One is RAY, one more is RAX. Either in this direction or this direction. But ideally speaking, this direction, because this beam will move in this horizontal direction, I think. It is objected by this reaction, that is RAX. Okay, next here, coming here, this is a roller support. One reaction develops, prevents the vertical motion of the object by this support. So this is first apply conditions of equilibrium. Okay, before that you convert this uniformly distributed load into a point load. 2 kilonewton per meter into 3, it will be 6 kilonewton. Apply here. Where are you supposed to apply? In rectangular component, in rectangle or in the uniformly way distributed load, it will act at the center. 1.5 this side, 1.5 that side. This is also uniformly distributed load about 1 meter. 3 into 1 is 3 kilonewton acting here at the midpoint, 0.5 meter that side, 0.5 meter this side. Next, move on to the conditions of equilibrium. Summation f of x is equal to 0. Then Rax in positive plus Rax minus 3. No other horizontal reactions acting here. Okay. Summation f of y is equal to 0. Ray minus 5 minus 6 plus Rb. So Ray plus Rb is equal to 11. Name it as equation 1. Next one is summation moment about the point A is equal to 0. 5 into 1 plus, this is in the anti-clockwise direction, so it is minus 10. 6 clockwise, so it is 3 plus 1.5, 4.5. 6 into 4.5 plus 3 in the anti-clockwise direction, so 3 into 0.5 anti-clockwise minus 3 into 0.5. This is 10 minus 10, which is equal to 0. Find out what is RB. Yeah. RB with respect to point A is anti-clockwise and the total distance is 6 meter, correct? So anti-clockwise I have taken it as negative. Find out RB, you will get 3.417 kilonewton. Okay. Substituting this value in this equation, that is equation 1, you will find out what is Ray. Now like in the similar problem, previous problems we solved similar way. Ray you know, Rax you know, find out the resultant of these both forces. Ra is equal to square root of ax square plus square root plus ay square you will get 8.155 kilonewton as the reaction at A, and RB you will get it as 3.417. Okay, that is all for today. Stay safe. We'll with some more problems in the concept of trusses. I'll meet you in the next class. Thank you.